Okay, so to kind of start off this lesson about tangents, we're going to take a look at a pretty involved example here with a lot of things that you might overlook just looking at it quickly, but it's really helpful just to kind of mathematically think through a couple things. So in the diagram below, we have AB is tangent to the circle at point D. So point D is going to be our point of tangency. Some special things happen there. BE contains the diameter FE. So I'm just going to make a little point over there. FE is going to be our diameter. Then we have angle ABE equaling 50 degrees with a vertex at B. So lots of stuff going on in this example. Really want to make sure that you just kind of label things out, make sure you know what you're looking at. Let's do A. What is the measurement of angle BDC? Justify your answer. Okay, so we have a couple things that we can do here. First off, we are going to label off angle BDC as 90 degrees. Now, this is a little bit different from what we did in lesson 1, kind of quoting a central angle and an inscribed angle. We're going to say that this is 90 degrees because it happens at the point of tangency. So angle BDC, let's put a D there, DC equals 90 degrees. And our reasoning is since D is the point of tangency, but also it's because D is linked with C. D is point of tangency of radius CD. When we extend a line that connects to the center of the circle, so a radius, could also be a diameter, but in this case it's just a radius from the point of tangency, we are guaranteed that this is going to be 90 degrees. So we have a 90-degree angle here. Perfect. So we already have this one, and we have our justify. What's the measure of the central angle DCE? So again, now we're kind of looking for what our angle of DCE is. I'm just going to put kind of like a question mark right there because that's the one that we're looking for. There is a couple things that we need to do for this. First off, there isn't any sort of arc measurement for DE and an inscribed angle that we could use, so it's pretty difficult for us to figure out what our angle is going to be just based upon that. And what I do want to make sure that you know about here is even though we have angle something like, let's say ABE is 50 degrees over here, it's not really a good thing to say that that's an inscribed angle with the same arc measurement as angle DCE. So we don't really want to use that. Instead, what I want to do is I want to show you that we should solve for this angle first. We should solve for angle DC. I'm going to label it as B first. And the reason why we're going to do that is we're going to use this angle to then solve for the other one. Take a look at this picture here. We have D to C, and then we have B over here. And this makes a triangle. We have 90 degrees over here, and we have that this is 50 degrees. Well, we know that triangles have to add up to be 180 degrees. So if we add up 90 and 50, we're going to get 140. And if we subtract that from 180, we're going to see that this is going to be 40 degrees. So inside here, we actually have a 40 degrees. But due to angle DCE being supplementary, we know that we can take 180 and subtract it from 40. So since, this is going to be kind of our reasoning here, since angle DCE is supplementary to angle DCB, angle DCE will equal 180 minus 40, which was angle, of course, angle DCE, or DCB. I'll kind of label that there. This guy is actually this one right here. So because of that, angle DCE is going to be 140 degrees. Oh, DCE, yeah, 140 degrees because it's supplementary. So that's kind of a new one to do, but that is an angle measurement that we should sort of review about supplementary angles. And the reason why we know it's supplementary is because we have a diameter here. EF is a diameter that spans 180 degrees across this entire central angle here. So that's good too. Let's go on to C. What type of triangle is triangle CDE? Well, let's take a look at CDE. I'm going to redraw it just briefly. A little smaller, but I'm going to redraw it here to there. We got our C here, we got D, and we have E. What's cool about this is that CE and DE, they're actually exactly the same measurement because they are radiuses of the circle. And we know the radius of a circle is the same everywhere. So automatically, this should kind of frame our thinking about what type of triangle this is. There's only one type of triangle that has two sides that are the same. And by default, if the two sides are the same, then that means that the two angles need to be the same as well. This is an isosceles triangle. Oh boy, how on earth do I even spell isosceles? I'm not even sure myself. Isosceles, I think. I'll look at the spelling really quickly on this one. But anyways, what we want to make sure that we know about ISO, oh no, I forgot another S. I'll put an S in there. ISOSECELES. There we go. Isosceles triangle. Two equal sides because they're both radiuses and therefore two equal angles. So this is an isosceles type of triangle. Why do we know that? Well, we just kind of explained our reasoning. Angle or EC is a radius and CD is a radius, and therefore that's going to mean that they have equal sides, and therefore that's going to mean that those angles are going to be the same as well. And finally, let's go ahead and let's do the measurement of DEC. DEC. I'm going to label this one out one more time again so we know we're looking at D all the way to E and then all the way to C. And remember, we actually already know what angle DCE is. So I'm going to label this out one more time. I'm going to draw a little bit of a bigger triangle and give myself a little bit more room here. Here we go. So C, D, and E. And we know this angle here, we already solved for it back in a previous question. This was 140 degrees. Okay, so we know that this angle and this angle are the same. And we know that they all have to add up to 180. So if we know that these two are the same, I'm just going to call them, X. X is pretty easy to use. So I know that it's 180. I know that what we have here is 180 must equal to 140 plus, and it's actually 2x because they're my two angles. So let's subtract 140 from both sides, and I get 40 is equal to 2x. We can divide by 2 on both sides to get to what x is by itself. And we're going to find out that x is equal to 20. And if we go back to our question, angle DEC, we're going to see that that's 20 degrees. Angle DEC equals 20 degrees. Explain our reasoning. Well, again, this is our isosceles triangle. So if we have both of our edge lengths being the same, then of course both of our angles should be the same as well. And thus we're going to have 2x there. Once we solve for it, we get our 20 degrees. And that's a nice little question, involving lots of stuff coming from the point of tangency and then just doing some angle work afterwards.